Mean value theorem for derivatives. Super, super important, so I'm just going to come out with it and explain it. So what it says is if y is equal to f of x is a function that is continuous, which by now you should know means connected, on a closed interval from a to b, and then differentiable, so not only is it connected, but it has to be smooth. Otherwise, this theorem will not apply. So if it's connected on the closed interval from a to b, and then smooth on the open interval from a to b, that just means it has to be differentiable at its interior points. Then there is at least one point, at least meaning there could be more, but we're guaranteed at least one point in the interval, so we'll call it C, and it's an interior point, it's not an endpoint, at which f prime of C is equal to f of b minus f of a all over b minus a. Now remember, f prime of C, that's the slope of the tangent line, because that's what the derivative means. F of b minus f of a all over b minus a, that's the slope of the secant line. So what this is really saying, so I'm just going to say over here, i.e., if a function is continuous and differentiable over an interval, and we'll just say from a to b, there will be at least one point where the tangent line is parallel to the secant line, because there is one point where their slopes are equal. So that is where the tangent line is parallel, when the slopes are equal, to the secant line. So you're probably like, what the what? What does this matter? I don't even know what this means. So let's take a look. Alright, so what we're going to do is we're just going to see what the mean value theorem looks like. So here's my f of x, and I think you would all agree that it's definitely continuous because it's connected everywhere, but it's also differentiable because it's smooth everywhere. No sharp corners, cusps, or any vertical tangents. Now we just need to give it an interval, because the mean value theorem is closed on an interval from a to b. So I'm going to go ahead and pick a point here where x is -2. You can see that over here, x is -2, y is 7. And I'm going to pick another point over here where x is 1. You can see that right here. X is 1 and y is 1. Okay, so I want to look at the function only between the x value of -2 and 1. Now, what the mean value theorem says is that if the function is continuous, which this one is, and differentiable, which this one is, then there should be some point between -2 and 1 where the derivative, or the slope of the tangent line, is equal to the slope of the secant line. So let's go ahead and find the slope of the secant line first. So I'm going to go ahead and draw in my secant line here. That's the line that connects the point from A to B. And I'll go ahead and find the slope of that line. And so just watch this value here. So the slope of my secant line is -2. All right, now what I have to do is create a tangent line. So let's go ahead and get our tangent line in here. All right, there it is. Okay, right now, clearly I can see that the slope of my tangent line is nowhere near equal to the slope of the secant line. But also notice that my point tangent is like outside the interval also. And let me go ahead and get my slope on this line, and so we can compare them. So m is the slope of the secant line, and then m1 is the slope of our tangent line. So what I'm going to do is I'm going to drag this point so that it's inside the interval, because I'm only looking at the interval between -2 and 1. And okay, so like for right here, for example, my slopes are totally different. But I did notice earlier that when I was over, well, it looks like right here-ish, if I could get it right on there. But it looks like there's going to be a point somewhere around here, where x is like around 0.2, where the slope of my tangent line, my derivative, is equal to the slope of my secant line. In other words, the slope of my tangent line is parallel to the slope of my secant line. And you can see here, it was just about equal to -2. But there was actually another point. It was up here, because remember it said only at least one point. There could be more than one. Just right. I keep passing over it, but right around here, where x is right around -1.5, I can see that the slope of my tangent line is almost -2. And if I could get this to trace exactly right, there will be a point where the slope of my tangent line is equal to the slope of my secant line. In other words, there will be a point where my tangent line is parallel to my secant line. In other words, there will be a point where the instantaneous rate of change is equal to the average rate of change. That's what the mean value theorem says. So example 1 here is wanting us to use the mean value theorem and just to kind of see how it works. So part A wants us to show that the function satisfies the hypothesis of the mean value theorem, which, if you recall, the hypothesis is that the function has to be continuous on the closed interval from a to b, meaning all the values are connected, and then also differentiable, meaning all the values are smooth, on the open interval from a to b. And in example 1, my a and b are 0 and 1. So what I'm going to do is actually sketch the graph of x to the 2/3 just to see if it is in fact connected and then also differentiable. So if you recall, this is the kind of graph that kind of looks like wings. It's got a point at 0, 0. It has a point at 1, 1 and a point at -1, 1. And it kind of goes like that. Yeah, it's a little bit sharper. Here. And it has that cusp right there at x equals 0. So I can see that, and oh, and also I'm only looking on the interval from 0 to 1, and it's a closed interval, so I'm looking from here to here. And I'm ignoring everything else. So from there to there, the function is clearly continuous, like all the values are connected. There's no jumps or holes or asymptotes between 0 and 1. It's also clearly differentiable because it's very smooth from 0 to 1. There's no corners, no cusps, no vertical tangents. So what we can say is that f of x is continuous on the closed interval from 0 to 1, and it's differentiable on the open interval from 0 to 1. Okay, so that means that we're guaranteed at least one value of c that satisfies the mean value theorem, which again says that there's at least one point where the derivative, or the slope of the tangent line, equals the slope of the secant line, the average rate of change. So first thing I'm going to do is find the slope of the secant line, which in this scenario would be f of 1 minus f of 0 all over 1 minus 0. So if I plug 1 in there, I get 1. If I plug 0 in there, I get 0 all over 1 minus 0. So the slope of my secant line is 1. So what I want to do is see if there's a point where my derivative, or the slope of the tangent line, equals that. So I'm going to find the derivative, which would be a simple power rule. So it's 2/3 x to the -1/3. And when we're setting that equal to stuff, it helps if I can see what's in the numerator, what's in the denominator. So I just recall that it's 2 over 3 x to the 1/3. And then I'm going to see if there is ever an x value that would make this fraction equal 1. So I'll solve this by cross multiplying. I'll multiply the 2 and the 1, and then the 1 times 3x to the 1/3. And so I get 2 equals 3x to the 1/3. Divide both sides by 3, and then raise both sides to the 3rd power to get rid of the 3rd root. So we're using an inverse function to undo the other function. So then I get x is equal to 2/3 to the 3rd power, and so x is going to equal 8 over 27, 2 cubed over 3 cubed. So that right there is my value of x, or my c value, I guess. And clearly that is between 0 and 1, so that's in my interval between 0 and 1. That would make the derivative equal to the slope of the secant line. So I don't have time in this video, but in class we're going to discuss what the meaning of this number is, and I'm going to have you write it in words. So just be prepared for that. Now, there are some what we call consequences or things that follow from the mean value theorem that are very important for you to know. One of them is using a derivative to know when a function is increasing or decreasing. What I want you to observe in this demonstration is how you can use the derivative to tell if a function is increasing or decreasing. So just as a quick reminder, a function is increasing when the y values are going up as the x value moves right. So x is going right, the y value is going up. That means the function is increasing. Then a function is decreasing if the y values are going down as x moves to the right. So we never go to the left. We always think of it as moving to the right. So if the values go up as x moves right, then the function's increasing. If the values move down as x goes right, the function is increasing. Now let's see how the derivative comes into play. So again, as a reminder, the derivative is the slope of the secant line. So let's take the derivative is the slope of the tangent line. So let's just take a look at what our slopes of tangent lines look like as a function is increasing versus decreasing. So what I want you to keep your eye on is this value here as I move along the curve. So let me start down here. So I'm starting to the left. So right now my slope is positive. I'm going to move to the right, and as the function is going, so I'm going to move to the right, and as I move the x values to the right, the slopes all stay positive, and then they're positive, 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 and then right when I get up to the top here, right where the function hits a maximum value, the slope is going to hit 0. The derivative is going to hit 0. Now, look at the values of the slope as the function begins to decrease. They're all negative. These slope values are all negative, so watch these numbers over here. The entire time that the function is decreasing, the slope is negative. And then as I get toward that minimum value, the slopes begin to level off and approach 0. And then as soon as the function begins to increase again, the values of the slope become positive again. So as the function's increasing, the values of the slope are positive. Now, another thing to look at. So again, I'm going to move from left to right. If the function is going up from left to right, the slope is going up. These are positive slopes. They're increasing. If the function is going down, the slopes are going to be going down. The tangent lines are going down. And then again, the function goes back up. The slopes, the tangent lines go back up. So if the derivative, which is the slope of the tangent line, is positive, the function must be increasing. As soon as that derivative turns negative, that means the tangent line is facing down. That implies that the function is going down. The function is decreasing, and vice versa. So to summarize what we just observed, if the derivative of a function is greater than 0 or positive at each point in an interval, then that implies that the function is increasing on that interval. Likewise, if a derivative is negative or less than 0 at each point on an interval, then the original function f is considered to be decreasing on that interval. Okay, now that's one consequence of the mean value theorem, is using the sign of the derivative to predict the direction of the function. Another thing this tells us is that if f prime of x equals 0 for all x on an interval, then the function, the original function, must equal a constant That's the only way a derivative could remain 0 over an entire interval. So I'll just give you a quick example. Let's say we had f of x equal to some number, maybe we'll just pick lucky number 7. The graph of f of x equals 7 just looks like a horizontal line that goes through the y-axis at y equals 7. So if you were to try and find, okay, the derivative at any point on an interval, so let's just pick the interval from like -3 to 3, so we're just looking at the graph from there to there. If I were to pick some x value in here, say this one right here, and I wanted to find the slope of the line tangent to the curve there, well, the line tangent to the curve would just be horizontal because it would just lie right on top of the graph because the graph is already horizontal. So the derivative would be 0 there. And if I picked any other point in that interval, the derivative is going to be 0 the entire time because the graph itself is horizontal, so you put a tangent line on top of it, and the tangent line is going to be horizontal, meaning its slope is going to equal 0. So basically, if your derivative is 0 all the time, then your function must have been a constant. The other consequence of the mean value theorem is that if functions have the same derivative, so let's say that you have f prime of x is equal to g prime of x on some interval, then for some constant c, the original function f of x must be equal to the original function g of x with the exception of a constant. So an example of this corollary is, let's say you had g of x equals x squared plus 3x. And then you have f of x which equals the same thing as g of x but plus a constant, so x squared plus 3x plus 5. So here's our g of x plus a constant. Well, if you were to find the derivative of g of x, if you were to find g prime of x, it'd be 2x plus 3. Similarly, if you were to find the derivative of f of x, it would also be 2x plus 3. So even though these functions differed by a constant, they ended up having the same derivative. So this is going backwards, saying, okay, if you end up with 2 of the same derivative, that must meant that the functions were similar except for differing by a constant. Now we come to examples that are going to help you with the bookwork. These first two that I have are going to help you with 19 through 24, and they are more related to the mean value theorem. So in example 2, it gives us this equation and then this interval. It wants us to write 2 equations, one for the secant line and then one for the tangent line. Now remember, to write an equation of a line, you need a point and a slope. So in part A, I have 2 choices for my points. I could either use A, f of A, or B, f of B. So let me see which one would be easier. So I'm going to figure out what f of 1 is. F of 1 is the square root of 0, which is 0. So I have the point 1, 0, or I could use f of 3, which would be the square root of 2. Not so fun. So I'm going to use the A, f of A point, the 1, 0. Now the slope of the secant line is when you just take the change in y and divide that by the change in x. So I'm going to take the rad 2 minus 0 all over 3 minus 1, which is rad 2 over 2. And all I need to do now is plug that into point slope form. And there's our answer for part A. Okay, so then for part B, it wants us to write the equation of the tangent line. So, oh, not just that, but the tangent line that is parallel to the secant line. So I need to find, first of all, where? I need to find my point. And that's going to happen when the slope of the tangent line is equal to the slope of the secant line. That's when they're parallel. So let me go ahead and find my derivative first. So first I'm going to think of f of x as x minus 1 to the 1/2. Then my derivative of that would be 1/2 times x minus 1 to the negative 1/2, and then times the derivative of the inside, which is 1. So that is going to be 1 over 2 times the square root of x minus 1. And then I'm going to set that equal to rad 2 over 2, and I'm going to move up here. So here's my slope of the tangent line, and here is my slope of the secant line. I'm going to set them equal in order to make them parallel. And I'm going to solve by cross multiplying. So I'm going to get 2 is equal to 2 times the square root of 2x minus 2, because I can, the two things that are inside a radical I can multiply together. And then I'm going to isolate the radical. So I'm going to divide by 2, and then I'm going to go ahead and square both sides. And then I get 1 is equal to 2x minus 2. Add the 2 over, I get 3 is equal to 2x, and so then I get x is equal to 3/2. So that is the x value where the lines are parallel, where the slopes are both equal to rad 2 over 2. But I need to find the y value so I can do my equation. So then I'll do f of 3/2, which is the square root of 3/2 minus 1, which is the square root of 1/2, which is basically rad 2 over 2. And then I'll go ahead and do the equation of the line using this x value, that y value, and then my slope, which is also rad 2 over 2. And there is our answer for part B. And we're done. Okay, then I have another mean value theorem question, which is asking for something a little bit different. It wants us to show that this actually does not satisfy the hypothesis of the mean value theorem. So if we revisit the hypothesis of the mean value theorem, that says that the function must be continuous and differentiable on this interval from 0 to 3. Let's go ahead and sketch a graph. I'm going to do part B first, and then we'll see why it does not satisfy the hypothesis. So if I were to graph the square root, the absolute value of x minus 1, it would shift to the right 1, and then it makes that absolute value shape, which is that of a V. And since the number in front here is a 1, the slope is positive 1 on the right and then negative 1 on the left. But if you recall, I'm only looking on the interval from 0 to 3, so I'm just looking from here to there. And I'm pretty much going to ignore everything else. I'm just looking from here to here. Well, it's definitely continuous because it's connected the whole time, but right here where x is 1, we have a corner. And so it doesn't satisfy the hypothesis because it's not differentiable on 0 to 3. So this is the answer to part A. Not differentiable for all x in the interval 0 to 3. So it fails. So in other words, this is not guaranteed. The mean value theorem is not guaranteed to hold because this function was not differentiable for all x in the interval. Okay, then we sort of did part B, but it wanted us to also graph the line through the points A and B. So this is A and that's B. So if I were to sketch the line through those points, it would look something like that. So that right there is our secant line, because it connects the two endpoints. And then in part C, it wants us to find any values in between 0 and 3 where the derivative would be equal to the slope of the secant line. So let's go ahead and find the slope of the secant line, which was f of b minus f of a all over b minus a. So f of 3 was 2, f of 0 was 1, and then all over 3 minus 0, so that's 1/3. And you can also kind of see that by looking at the graph. It goes up 1 and then over 3, 1, 2, 3. So the slope of the secant line is 1/3. So now what we want to do is we want to see if there's a point where the derivative, which is the slope of the tangent line, ever equals 1/3. So what we have to notice here is that these are two lines being connected at a corner. On the right side, so from 1 to 3, the derivative, which is the slope of the tangent line, is just 1, because it's going up 1 over 1, up 1 over 1. So for x from 1 to 3, the derivative is equal to positive 1. And then between 0 and 1, the derivative, which is the slope of the tangent line, is negative 1. So it's going to be either one of those two things. It's either negative 1 and then it abruptly changes and becomes positive 1. So it's never going to equal 1/3. So there is no value c such that f prime of c equals 1/3. And so you can see that the mean value theorem did not apply to this function because this function did not satisfy the hypothesis in that it had the corner at x equals 1. It was not differentiable for every point between 0 and 3. These next two examples apply more to the second concept of the day, which is using the sign of the derivative to tell where the function is increasing or decreasing. And we're also going to find local extremes. So we're going to combine our process that we used in the examples in 4.1 with these examples here. So if you recall, step 1 was to find the derivative. So that'll be the same step 1 we do for these questions. So the derivative here is 2x minus 1. Step 2 is to find where the derivative is either 0 or undefined. So we're going to find our critical points. So I'm going to set the derivative equal to 0, and I can see that it will be 0 when x is equal to 1/2. And there are no points where it's undefined. Okay, now here's where step 3 is a little bit different. We're going to create a sign chart. And we're going to do that by splitting the x-axis over the endpoints if there are any, and the critical points if there are any. So let's go ahead and set up a sign chart here. And we're going to check the sign of the derivative and then the direction of the original function. So I only have one critical point and I have no endpoints. So that means it's going to go from negative infinity to infinity. So one of my intervals is from negative infinity to 1/2. That's like the left-hand side. My other interval is from 1/2 all the way to positive infinity. That's the right-hand side. What I want to do is pick a point inside the interval and plug it into the derivative to see if the derivative is positive or negative. So maybe I'll test the point 0 because that's in between negative infinity and 1/2. And when I do that, I get 2 times 0 minus 1 is negative. So I get the derivative is negative. Now we learned earlier that if the derivative is less than 0, the function must be decreasing over that whole interval. Okay, now I'm going to test another point here between 1/2 and infinity, so maybe I'll test 1 in the derivative. So you check with the derivative because you're finding if the derivative is positive or negative. So I put 2 times 1 is 2, minus 1 is 1, which is positive. The derivative is positive on that entire interval, which means the original function is going up. It's increasing over that entire interval. So that tells me, that answers my questions for both A and B. I can see here that I have an absolute minimum at x equals 1/2. And now I know for sure it's absolute because the function is going down this entire time. There was never any point where it's going up. It's going down this entire time, stops here. This must be its lowest point because then afterwards it goes up the entire time. So it looks something like this. Down and then up. So it has an absolute minimum at x equals 1/2. So our answer for part A is we have an absolute min at x equals 1/2, and then it's equal to, let's see, equal to 1/2 squared minus 1/2 minus 12. So that's 1/4 minus 1/2, which is negative 1/4 minus 12. So the minimum would be equal to negative 12 1/4. That's the answer for part A. Then for part B, which I guess I'll write up here, the interval where it's increasing, that's this whole interval here. So it's increasing from negative infinity to 1/2. It's decreasing from 1/2 to infinity. Oh wait, I mixed that up. Oh, sorry. Increasing is going up. So it's increasing, sorry, right here from 1/2 to infinity, and then it's decreasing here from negative infinity to 1/2. So the steps 1 and 2 are the exact same that we did in section 4.1. The only thing we're adding in 4.2 is this sign chart. And then I wanted to do one more example that's using the same steps but with a little bit more complicated function. So step 1 is to find the derivative. But before I do that, let me just distribute this x term here. So this is going to become x to the 4/3 plus 8x to the 1/3. Because here you could think of this as x to the 3/3. And when you're multiplying bases, you add the powers. And then, yeah. So my derivative would be 4/3 x to the 1/3 plus 8/3 x to the negative 2/3, because I multiply the 1/3 to the 8 and then subtract 1 from it. Now what I want to do is combine these together, because what I'm going to have is two fractions, and I have to set this equal to 0, and it's a lot easier to do that if I've combined it as one fraction. So I'm going to get a common denominator, and I'm just going to multiply the bottom of this fraction by x to the 2/3 so that they'll both have 3x to the 2/3. And so what I'm left with is, this ends up being x to the first power. So it ends up being 4x plus 8 all over 3x to the 2/3. Okay. Step 2 is to find where that is equal to 0. So basically set it equal to 0. And again, a fraction is only equal to 0 when its numerator is equal to 0. So we'll just set the numerator equal to 0, and that will happen when x is negative 2. Also, we want to find when this is undefined. So 4x plus 8 over 3x to the 2/3 does not exist when x equals 0. So these are our two critical points. Then in step 3, we split up the number line, like we did here, over our endpoints if we have any, and then critical points if we have any. Well, again, I have no endpoints here because the domain is all real numbers, so it doesn't stop or start anywhere, and I wasn't given an interval. So basically I'm going to split it up over these two values. So in the first part I have the derivative, so I can check if it's positive or negative, and then in the bottom I have the function, which is going to either be increasing or decreasing. So my first interval is going to go from negative infinity, since I have no endpoint, to negative 2. Then there's the interval in between these points, negative 2 to 0. And then there's the interval from 0 to infinity. Now here's where I pick a point. Pick a point less than negative 2, plug it into the derivative. So maybe I'll pick negative 3. So I'll plug negative 3 in here. And on the top, I'd have negative 12 plus 8. That's a negative number. On the bottom, no matter what I plug in here, it's always going to be positive because I'm squaring these values. So this will be positive no matter what. So when I plugged in the -3, I had a negative on the top and a positive on the bottom. So a negative divided by a positive is a negative. So notice I don't need to know what the derivative actually is, I just need to find out if it's positive or negative. When it's negative, the original function is decreasing. Now I'll pick a number between -2 and 0, like -1. So here we tested -3, here I'm testing -1. If I plug -1 in there, I get -4 plus 8. That's a positive. And then the denominator is positive no matter what I do, because again, x is squared. So positive divided by positive is positive. The function is increasing. Now I pick a number between 0 and infinity, like 1. Plug 1 in there, I get 4 times 1 is 4, plus 8, that's positive. The denominator is always positive. Positive divided by positive is positive. So the function is still increasing. So I know here that I have an absolute min at x equals -2. And I have no extreme value at x equals 0 because the function did not change direction. So the answer to part A is that I have an absolute min at x equals -2, and I'm not going to bother to figure out what g of -2 is at this point. And then for part B, sorry, this is kind of everywhere, I'll put part B over here. The function is increasing all the way from -2 all the way to infinity because it never stopped increasing. It never changed direction at 0. And then the function is decreasing from -infinity to -2. Oops, sorry, there we go. Okay, now the last page we're going to save for class, so please bring this with you and we're going to work on parts A and B together in class, and I'll see you there.